Dear friends, welcome. I am Taha Alper, the teaching assistant of the Physics 505 course. During the regular semester, we were solving some problems related to the topics we cover in the course, and we have completed the solutions to the very first homework. But the second homework has been extended due to the health issues. So in this session now I will try to provide you the solutions of the second homework. This homework has been dealing with the three significant matters. One of them was the method of images, and we will be applying that method for three different cases in this station, and others were to be the Laplace equation and the Poisson equation. The Laplace equation, which turns out to be the equation for the electrostatics under the free space, for the free space, while we have some existence of charge in the case of the Poisson equation, which leads us to use the Green's functions, right? So let me start with the very first problem now. Here I'm already assuming that you have already read the problem beforehand. You can also go over it quickly. Here we have an infinite plane, and on that, above that infinite plane, we have a charge over here at a distance of d, whose charge is q. Okay, and we make sure that this infinite plane is kept in a ground potential, right? Under these circumstances, we expect to see some charge distribution, some induced charge along the surface of that infinite plane. But one of the most important things to realize here, the E field distributes itself at the above side, at the, let me put a coordinate system here, at the for the region where y is positive. We have the existence of the E field, but underneath there's no E field. That's one of the things due to the geometry of our problem. Okay, under these circumstances, we need to derive the surface charge density induced on the plane, and we need to plot it. And the force between the charge and the plane by using the Coulomb's law. The total force acting on the plane and the work necessary to remove the charge from its position to the infinity, and the potential energy between the charge and its image. So this is a very typical problem of method of images. In order to solve this problem, for instance, let me quickly draw a couple of E field lines. The important thing is to realize here, whenever I am on the surface of this conductor, I need to have the E field just perpendicular to the surface, right? Okay. How can I determine the surface charge density in the, given that the E field distribution in this fashion? Remember, on the surface of a conductor, if there exists a Gaussian surface defined as follows, since there is no E field along here, let me put a dummy variable of area A. The total E field will be along this surface, right? And in that case, EY A shall be equal to sigma A, the charge density divided by E0, which means that the E field, due to the existence of charge density, can be formulated as follows, which means that if I do calculate the E field, I can end up with the charge density in a simple fashion in this form. Okay, so if my purpose is to calculate the E field at the conductor surface, then by using that function I can extract the information of the surface charge density too. And that is I will do for the moment, but I will do it by using a method of images. In this case now its method is simple, its image is simple in this case. It's minus q at a distance of d, which makes sure that the whole potential at this surface is equal to 0. That's the whole idea. But remember that it's then 2D plane, so x, y, z, it's a plane at xz, so in fact the better picture shall be this one, right? And if I want to, for instance, calculate the electric field intensity at this point, let me use the cylindrical coordinates rho and phi. Okay, in fact let me change my coordinates to a proper one so that it is along this xy plane and it's z direction. In this case now my electric field along the z direction. Okay, how can I calculate the electric field at this point? Remember that wherever I am, my resulting E field should be along the z direction, right? However, to account for the contributions from here to there, right? Let me erase it. Sorry for the mistake. Let me put my rho over here, in fact, in order to make things simpler for a first step. Let me call this rho, and E field due to the existence of minus charges over here and plus charge shall be over here. Okay, so the horizontal contributions will cancel each other expectedly because it's a conductor. That cannot be a tangential component of E field during along the conductor surface. So that is what I need to calculate, and in fact the magnitude of these two guys are equal to each other. So let me call this a theta. So the E field, which is along minus z direction, needs to be equal to the E field due to the existence of Q at this point, Q divided by 4πe0 multiplied by 1 over r square multiplied by sine theta, and I also need to multiply it by 2 due to the plus Q E field. Okay, what is R here? R is nothing but d square plus rho square, so Q 4πe0 d square plus rho square. What is sine theta? Sine theta is nothing but d over d square plus rho square to the power of 1 over 2, which that multiplied by 2. So the Ez is equal to 2qd 4πe0 d square plus rho square to the power of 3 over 2. And of course its vectorial form is this one. It is along the minus EZ direction. Okay, if this is the E field, how can I pass from the E field to the charge distribution? The E field existence is due to the surface charge, the induced surface charge at the conductor surface. So I can just re-express it as E0 EZ, which is nothing but 2qd 4 pi d squared rho squared 3 to the power of 2. As a function of rho. Of course, there needs to be a minus sign over here, because the induced charge density is minus. Okay, nice. We can in fact cancel it further and write it down as this form. Nice. Okay, what about the B part now? What does it look like? It looks like a as a function of rho. Once rho is equals to 0, in fact, let me rewrite it as follows, because charge is minus here. It will be highly accumulated over here, and it will be symmetrical with respect to rho equals to 0. One goes as follows, and the other goes as follows. That's the surface charge density distribution. So it is much dense over here, and then goes like this. Nice. Of course, all of the charges at the very surface of the conductor. It's just to highlight the intensities with respect to rho. Nice. What about the B part now? At the B part, what we were asked to find the force between the plane and the charge by using the Coulomb's law. So all we need to do is to find this law, right? It is equal to 2D, and the F shall be equal to what? This is again plus EZ direction, Q square divided by 4PE0 2D square, right? That's the solution. It's a simple application of the Coulomb's law. But even though we claim that the force between the charge and the infinite conductor can be successfully pictured as the force between the charge and its image charge, let's try to make sure that this sort of an approach is valid. Let's try to make sure that we rederive the very same force between the charge and the plane by taking the whole integration over the charge and its interaction with the conductor surface. Okay, for this purpose now I will follow the following approach. You see, it is our infinite plane whose charge density is only a function of rho. It is phi symmetric, minus qd divided by 2 pi d square rho square to the power of 3 over 2, right? Let me quickly check. Yeah. Okay. And now my plus q over here, right? This is the origin of our coordinate system, right? And okay, at the point over here, rho, let me draw it over here, rho and phi. What is the force applied on it? Let's calculate that one. Rho and d over here, right? I have a, let's say, let me call it, for instance, we have this surface charge density, so on an area of dA, I have rho dA total charge, and dF is equal to rho dA multiplied by Q divided by 4πe0 d square rho square. That's the answer, right? Okay, this is the infinitesimal force dF, but it's not the whole story, because even though this can be calculated, what I need is the theta version of this, because otherwise the vectorial summation over the integration will be harder. But I also do know that the resulting force will be nothing but the aggregation of the forces perpendicular to the surface. So let me calculate the dFz by dF sine theta. Okay, and that is now being dAq 4πe0 d square rho square, and sine theta is nothing but d divided by d rho square to the power of 1 over 2. Okay, that is, I will integrate, of course, dA in cylindrical coordinates, rho d rho d phi. Okay, hence now total Fz, which is a summation over dFz, which is a summation over 0 to 2 pi, 0 to infinity, rho d phi multiplied by sigma rho q d 4πe0 d square plus rho square to the power of 3 over 2. Okay, that is the integration that I need to take. And also remember that this is the expression for sigma rho. Okay, since we have a phi symmetry, I can take this out as 2 pi. Okay, and the rest qd divided by 4πe0 can be taken out also, right? 0 to the power of 0 to infinity rho sigma rho d rho divided by d square rho square 3 to the power of 2. Let me place sigma rho now. There will be another contribution of qd, right? So now qd 2e0 minus, let me check, qd again 2 pi, but the rest cannot be taken outside. So now 0 to 2 infinity rho d rho divided by d square rho square to the power of 6, I think. Let me quickly check if I have done it correctly. I'm sorry, not 6, it should be equal to 3. Rho d rho, yeah, q square d square 4πe0, yes, q square d square 4πe0. There's a minus sign here, but I think we can correct it later. No, that shouldn't be. I mean, because we are taking the magnitude of the sign here. I have already handled by assigning some vector over here. So this integration is now my matter of interest. O squared to the power of 3. We can simply just assign it to be equal to u, which means that du will be equal to what? 2 rho d rho, which means that this integration becomes from d square to infinity du over 2 u cube, right? Which means that it is equal to 1 over 2 divided by minus 2 d squared to infinity, which means that it is equal to 1 over 4 1 over d4. Okay, so if we just put this back, f shall be equal to ez q squared d squared 4 pi e0 d4, which means that it is equal to ez q squared 4 pi e0. Sorry, there should be a 40 here. To the square, and which is equal to the f found in part. What was the part? B. So we have checked by explicitly calculating the Coulomb interaction between the plus q and the induced surface charges. We have taken the integration over the whole surface of the infinite plane. Hence, we have ended up with the very same result. So it seems like method of images is working just fine for the forces too, at least for this special case. Okay. Now, let's discuss the following. Let's discuss the D part of this problem. On D part, the work necessary to remove the charge Q from its position to infinity. Let me be quick about it. I think we got the idea for this problem. In this problem now, we are taking this from x, starting from D to infinity. So the surface, the image charge will also go away. Hence, we need to make sure that this interaction also does change while we move our point charge here. So f shall be now equal to q square divided by 4 pi e0 to x square, right? And work is nothing but f dx from d to infinity, right? Let me use this path, it's better, and which we can re-express it as q squared divided by 16p e0 1 minus x 1 over x from d to infinity, right? Which just turns out to be q squared divided by e0d work. This is how much work we need to do on the charge in order to make it free from the interaction of the conductor surface. What about the E part? The E part asks us the potential in between the two. Remember, in usual cases, the potential energy gives us how much of the work that we need to complete in order to make it free, in order to move it to the infinity. However, in this case, at first sight surprisingly, but later understandably, is equal to Q squared divided by 4PE0 2D, right? Because the difference between the 2D and it is nothing but R here, and it is equal to minus Q square 8PE0D. You see, in magnitude, this potential is less than what needs to be done at the above part. Why is it that way? Because this potential value gives us the how much work we need to do once I take this plus Q and bring it to the infinity. Okay? While minus Q stays constant. That was the whole idea. But in method of images, if we were calculating, for instance, the work we need to do, given that there exists a minus Q over here and staying where it is, and I'm taking plus Q to infinity, this is how much of work, the magnitude is how much work that I need to do. However, as I get out of the closeness of the interaction to the infinite plane, I need to do less amount of work, because the method of images tells that once I put it over here, X, it gets the method, the images also gets far away. Okay, so expectedly, I'm sorry, this is greater than. Expectedly, the potential, the work we need to do is greater for the constant of minus Q with respect to the one that I place a infinite plane. Okay. Okay, very nice. Let me pass to the second question now. In this problem now, in this problem now, I will be studying again the method of images, but in this case now, it's for a sphere. Let me place a sphere over here. Okay. In this sphere now, it's at the origin, and let me assume that I place my Q over here at a distance y. Let me also I'm sorry, let me delete this. Okay, this is much better now, I think. Yeah. Okay. This is the origin of the circle. I am placing my plus Q over here at point Y, and I am given that the whole circle surface is grounded. It has the very same potential. Under these circumstances, what is the image charge of it, so that I can calculate the potential inside the sphere-induced surface, charge densities, etc. That's the idea. I will be quickly deriving we expect to see some minus sign over here, but let me just denote it by Q prime, and let me denote its distance as Y prime. Okay. What I expect to see is the following. For instance, at this point, I need to make sure that the potential is 0, and also at this point, I need to make sure that the potential is 0. Okay, by using this information, and also given that the radius is a, I can draw the following equations, right? Q at this point, the potential is Q for P is 0, a minus y plus, plus, what's happening? Q prime 4 pi e 0, what is it? Y prime minus a is equal to 0 here. At this point, I have Q 4 pi e 0 a plus y plus Q prime 4 pi e 0. Let me check. Y prime plus a is equal to 0. Let me quickly check. Yeah. Which means that Q over a minus y plus Q prime y prime minus a is equal to 0, which is Q a plus y plus Q prime also equals to 0. Two equations, two unknowns. I can always extract to find out what are Q's and Y's, and if you do this gently, you will be ending up with y prime is equal to a squared divided by y, and Q prime is equal to minus Q a divided by y. I strongly suggest you to go over these. It's a simpler method to find for a spherical surface. It's a image charge. Okay, if this is given now, I can proceed to my purposes, right? For instance, I can calculate the total charge density inside the sphere by the following method. Phi total due to Q and Q prime, right? For the Q shall be equal to, let me choose a R over here, okay? An arbitrary point inside the sphere. Let me call this a gamma, which means that the potential due to this one will be equal to 4 pi E0. Its distance can be found by the cosine theorem, right? So it simply gives us r squared plus y squared minus 2ry cosine gamma to the power of 1 over 2, of course. And then for Q prime, we have minus AQ 4 pi E0 y, and the distance, in this case now, r squared plus y prime square minus 2ry prime cosine gamma 1 over 2, I think. So writing it down in a more acceptable fashion, Q divided by 4 pi E0 is equal multiplied by r squared plus y squared 2ry cosine 1 over 2 minus a over y r squared plus y prime squared minus 2ry squared cosine gamma is the potential. Potential at where? Potential at R gamma. Very well. Now what about the E field, right? E field at the surface. That is, we would like to find out. For instance, I do know that it is perpendicular to the circle surface, spherical surface, but how can I find it? It is again the very same idea, right? We will be using sigma E0 shall be equal to E at the surface, okay? Perpendicular to the surface, of course, but E is nothing but phi total divided by R at R equals to A, right? That's the definition of the electric field. It's the gradient of the potential. Since we are seeking for only the R components, because which is the only component that is perpendicular to the surface, right? So this is the definition, which means that I can calculate the electric field by surface charge density by minus E0 delta phi divided by delta R, where we evaluate R at A. Okay, so I need to take the derivative of this. By the way, there's something wrong here. I just have realized this should be in this form. Let me take the integration with respect to R. Okay, this is quite a long algebra, but once I am done with this, I will be given a break. So delta phi total divided by delta R is equal to Q 4 pi E0. How can I take the integration of this? Minus 1 over 2, it's the power. Derivative inside 2R minus 2Y cosine gamma Ry cosine gamma to the power of 3 over 2. But I need to multiply it by minus 1 over 2, right? It was the power, taking it, lowering the power 1 by, and it's inside the equation. And the similar idea goes for A over Y. In this case, 2R minus 2Y square cosine gamma minus 1 over 2 divided by this one. Okay, 1 over 2's will cancel each other. Q over 4 pi is 0, right? Minus, let me put the minus sign out. R minus Y cosine gamma divided by this expression minus A over Y cosine gamma divided by this expression. Of course, I need to evaluate it. At R equals to A. But before doing that, let me re-express the whole in this form. This can be written down as y over y square R square plus 9. No, let me keep it in this form. I will place the a's later. Okay. Okay, let me evaluate the whole expression now. At r equals to a minus q 4 pi e 0 a minus y cosine divided by a square plus y square minus 2ay cosine gamma to the power of 3 over 2 minus a over y minus a over y, and then a minus a square divided by y cosine gamma divided by, again, a square plus, I am placing the y prime, a square divided by y square minus 2a square y cosine gamma 3 to the power of 3 to 3 divided by 2. Okay. There is one step left now. So this whole expression can be reduced to minus q 4 pi e 0 a minus y cosine gamma minus a over y cube divided by a cube a minus a square y cosine gamma divided by a square y square minus 2ay cosine gamma 3 to the power of 2. How shall I pass from here to there? I have only re-expressed this and put it into this form. It just turned out to be an extension of y squared divided by a square, right? I am taking it to the upper side and it ends up with this. So now the above part can be further eased. 4 pi e 0 a minus y cosine gamma minus y squared divided by a plus y cosine gamma. These shall cancel. At the end I have qa 4 pi e 0 1 minus a square divided by y square divided by the whole expression now. What was it? Yes, a square y square 2ay cosine gamma 3 over 2. Okay, this was the derivation with respect to R evaluated at A, and the total charge density now can be found by, as a function of gamma and y, is equal to q over 4 pi a square a over y multiplied by 1 minus a squared y square at this whole expression. 1 plus a over y square minus 2a over y cosine gamma 3 to the power of 2. That was the purpose. Okay. What is the force between these two? It is again the very same idea, the magnitude and the direction of the force acting on Q. It is the Coulomb force between the charge and its image, and it's nothing but the following. If Q prime, it is along minus ER direction, right? Q prime 4 pi E0 R1 minus R2 square, which is minus ER Q squared A over Y divided by 4 pi E0 A squared divided by Y minus Y square, which can be written more properly as follows. F is equal to minus ER Q square AY 4 pi E0 A square minus Y square to the power of 2. As a last discussion on the D part, we were asked to find if instead of the sphere to be constant 0, let's assume it to be V is equal to V0, it's asked. But the idea for this part is the following. In classical electromagnetism, the potential value itself can be shifted, and it does not make any difference in physical reality. The physical reality of the classical electromagnetism is are the charges and the fields, right? So we do not expect to see any change in the reconfiguration of the charges, but we will expect to see a shift in the whole potential values. So instead of now the original value of phi I, the first situation, the new phi will be nothing but adding by V, but the induced charge of this configuration will be the one with the zeroth case. Okay. What about for the case that instead of the charge, yes, again kept at the same constant, the same at the potential, but also have some plus Q on it. In this case now, the idea is the following. How shall the potential shift in this case? Remember, the plus Q induces overall minus Q at the inner surface of the sphere. Hence, since the total charge on the sphere is plus Q, at the above side I expect to see a plus Q plus small q charge. Okay. Hence, this shall be the potential of the surface. In this case, V prime is equal to Q plus Q divided by 4PE0, and the distance is the diameter A, as this is the new A now, as the shift in the potential with respect to phi 0 will now be this much, this V prime much. And induced charge density will be equal to, again, the proper it will be the same with the previous case, but of course total charge density will be the induced charge density will be this one. The total charge density at the outer surface will be shifted by Q divided by 2PA. That was my purpose. Okay. gamma outside plus Q2PA. Okay, these two examples were related to the application of the method of images. I think we need to be patient in order to find the surface charge density. The method gives us a nice expressions for potential, but in order to find the surface charge densities, remember they have some relation to the electric fields at the surfaces. So we need to calculate we need to take the gradient of the potential. In this case, we take the gradient with respect to the R component, and after quite an algebra, we end up with this surface distribution. Okay, thank you for your listening. Let's give a break here, and I will continue with the third and fourth problems in the next hour.